Okay, so good morning, guys. Today I would like to um, cover a topic that actually some logistical things because semester is flying by and we're not having a midterm this year. I don't think that this is a course that lends itself well or even sensibly to holding a midterm exam. So what I've told you is that we're going to do like a 24-hour data challenge. I'm not going to torture you guys. I think I know how I'm going to make it. It's essentially going to be like a homework, except that you have 24 hours to do it. It's going to be a math lab exercise. You're going to have a lot of instructions. There's going to be a lot of structure put into it. It's not going to be like a hackathon where you have to literally, you know, develop a bunch of code from scratch. It's going to be more like a fill in the blank type. So it's going to be structured. My plan is to have that be probably be assigned on April 6th. I want to do it before the break. It is possible that I can push it forward to the following week. The Wednesday would be the April 13th. I'm okay to do it that week too, as long as we do it before the break. So the way it's going to work, it's not going to interfere at all with our class time. It will just be, there will be a link put on Blackboard with some instructions and some starter code, and you'll have 24 hours to send me your solution. It's not going to rely on anything that it's going to be a continuation of everything that we've been doing so far. So there's not going to be anything radically different on it. I don't want to stress anyone out in this course. All I want to do is just test your basic knowledge of of the concepts in machine learning, and then basic understanding of how to actually deploy some of these. And because we're really only halfway through, again, I'm going to keep it very structured. So it's going to be, you should think of it more like as a homework where you have 24 hours to finish it. Okay, so watch for that announcement on Blackboard in the coming days. The other thing that I want to mention is kind of like I think we have 6 or 7 weeks left. And so what I told myself at the beginning of the year was that I really want to get you guys as much time with deep learning as possible. And so support vector machines are absolutely essential in any machine learning course. I want to finish this topic, and I'm thinking about after this jumping directly to deep learning, which is done in Python. There's also some unsupervised learning topics that I would really like to cover, like clustering, which I think is very useful. But I may, as I have been doing, I may go out of order. So this is everything we're doing now is supervised learning, where you're predicting Y from X. And I think I'll continue with supervised learning all the way through until deep learning. And then at the end of the year, I'll probably devote some time to unsupervised learning, which is kind of I think where the future of this field lies. Okay, so that's it for the announcements. I'm going to try to use preview as my for my slides today. So this is part 2 of support vector machines, and this is the part that covers what are known as kernels. So kernels are something that, kernels are something that you hear a lot about, and specifically there's something called the kernel trick, which I'll try to explain to you. And I hope that it doesn't take you as long to understand what the kernel trick is as it took me. because I didn't have like a formal education in this field, and I was kind of piecing things together as I went, I was really confused about what the kernel trick was. And so we cover that in this lecture, and hopefully it will make more sense than it did to me at first. I do want to cover the theory first, and then jump into some examples of how to actually implement these in MATLAB. So notation, nothing new here. We have a training set, and the ith example we're going to denote by superscript I, right? So superscripts are going to denote examples for both the features and the label, and subscripts are going to denote the dimension. So let me see if I can take a stab at annotating. If I have, let's see if I can use the free draw here. So if I have a data set, so this is the first example. So this is all one example. And then let's say that we have 10 features, right? This would be example 1, and this would be a vector. And then example 2 would be, I guess I'll draw the superscripts here. So the superscript means that this X belongs to the first data point. And this will be still 1. And then example 2 would be also a 10-dimensional vector, but would have a different superscript. So that's important because in kernels, so this is also example number 2 here, like this. Okay. That. And so the subscript just means within a given example, which feature. So you can think of the subscripts here as the pixels of your brain scan, and the Y's are discrete indicator of which class that brain scan, benign or malignant, belong to. All right. All right. So just to kind of refresh your memory as to where we left off last week. So the interesting thing about the math behind support vector machines is that the problem was formulated as you have two classes, and you want to draw a hyperplane that has the largest margin, and then the math of Lagrange multipliers essentially transform that into something that looks quite different, but is mathematically equivalent. And so what we saw is that our prediction, so the left-hand side here, this is the support vector machine's prediction for a new example X. So X here is just something in your test set that you're looking to make a prediction on. And what we saw is that prediction is a linear combination. It's a linear combination of inner products. So this superscript I here is indexing across your training set. So whenever a new data point X comes in, you compute its inner product with every training set example, and then you weight it by this Lagrange multiplier alpha. And the method is called support vector machines because many of the alphas end up being 0. And so the alphas that aren't 0 correspond to the quote unquote important examples in your training set. So if the corresponding alpha is 0, then it doesn't matter. It doesn't matter how the new data point compares to that training example. But if the alpha is large, let's say, then it means that that training set example is critical towards making the decision. And so I will take one more stab here at annotating, this time with lines. just to make sure everyone understands what this equation is doing. I'll switch colors. So this will be class number 1. And this will be class number 2. And perhaps the support vector machine in this case would be something like this. That would be your decision, that would be your maximum margin hyperplane. And the thing that's important to understand here is that each of these, so like the alpha here, this alpha I will probably be equal to 0. So every example has an alpha. Oops, this is, when am I going to learn not to copy and paste in annotations? So this alpha I would also be 0 here, but this alpha I would be bigger than 0. So they're always going to be positive, by the way. That's another thing. The alphas are, and have to, by definition, are positive. So this alpha will be positive, and probably this alpha, these alphas will be positive. Why? Because they're close to the decision hyperplane. And so the idea is when a new data point comes in, it's being compared to the examples in your training set that that have a a non-zero alpha or Lagrange multiplier. So a couple of things about this that may not be apparent when you look at these just as an equation. Number one is that this can become very costly computationally because you want your training set to be large. And so if you have a data set that has 100 million brain scans, then you unfortunately have to implement this for every example in your test set. You have to compute the inner product between that example and all 100 million training set brain scans. So this is important because even though your W, even if you're separating hyperplane, it may only be a few dimensions. But if you're doing it this way, if you're doing support vector machines with these inner products, then it doesn't really matter, because what you're essentially doing is performing a bunch of similarity measures between data points. And so this is one thing, I think I mentioned this last week. I was very confused when I saw the implementation of support vector machines, and I didn't see a W anywhere here, right? On the right-hand side, there's no W. And it's kind of being absorbed into these inner products. And as a result, it's a totally different computation. So the second equation here, all it is just a change in notation. So we've expressed the inner product between the training example and your test example in this with this norm notation. So this is these brackets here denote any kind of inner product, any norm between two vectors. So you should think of this, the reason this is done is because the inner product may be thought of as a way of measuring similarity between two vectors. So for example, if the two vectors have unit norm, then it is just similarity. Then it's just, that the inner product between two unit vectors, it's just the angle between those two vectors. So if the two vectors are the same, then the inner product ends up being 1. And if the two vectors are orthogonal, which is kind of the geometric equivalent of unrelated, then that inner product will be 0, right? And if the inner product is 0, then there's no weight being contributed to the prediction by that training example. And if there's one thing you take away from this, it's what's written at the bottom here is that support vector machines are essentially template matchers. And so you have a template for each class. That template is defined by the support vectors of each class. And you use that template to make predictions on new data. And that's both a wonderfully intuitive result, but it's also, it also explains why a lot of these methods fail either in very high dimensions or in problems where there's a lot of variability within classes. So things like, I've talked about images a lot. You can take an image of the same object and have it look totally different in pixel space. And that's why template matching isn't always a good idea. It may actually be pretty sensible for a lot of biomedical applications, by the way. It's the application where template matching fails is really in these like computer vision, natural language processing. There's probably others that I'm missing, but a lot of these problems are inherently just very variable. But my experience with data sets, medical data sets, is that often these classic shallow learning techniques, they work pretty well. And that may be because you don't have maybe the variability problem as much as you do with, for example, if you compare natural images with brain scans, right? Or any kind of medical scan. So natural images that are, let's say images that are uploaded to Google Images or something, they're taken by all kinds of different people. It's a very uncontrolled data set. And so there's going to be changes in lighting and pose, etc. On the other hand, if you have a database, if you have a data set of MRI scans, well, there's a lot of consistency between how each of those brain scans was collected, right? So the MRI technician is always aiming to put the volume inside the middle of the field of view. We don't want to have too much white space. There's no lighting problem. There's the differences between contrast are, relatively minor compared to what you see with lighting differences in images. And so I think that you should always consider when choosing the algorithm that you want to use, you should always consider the nature of the data set. And so a lot of the, I think a lot, and this is, I can't stress this enough. The field of machine learning has been, in the last 20 years, really developed in the context of image processing. And so a lot of the knowledge that has been gained in that context. And so be careful with generalizing that to other types of data, because it is a very, the deep learning developments are very much driven by advances in image processing, in image classification. And so my experience with, mostly neural data, but not just neural data, is that support vector machines and logistic regression work very well, especially logistic regression, actually. It's a remarkably robust algorithm. Okay. I will move on here. Okay. Now we're getting to the kernel trick. So, right. So let me think of an example here. Other than a brain scan, because the brain scan here doesn't really translate well. But the idea behind kernels is that you have some measurements of your object, the thing that you want to make a prediction on. And let's say, let's try to do something like you have a bunch of health measurements on an individual. Let's say you have, let's say you have, height, weight. Let's even have BMI, even though that's redundant here. Say age, resting heart rate variability, exercise frequency, whatever, daily caloric intake, all kinds of things that will be hard to get from everyone, but let's say you have them. And you want to predict, let's say you want to predict life. Oh, I didn't mean to change the font on that. Oh, all right, never mind. Let's say you want to predict lifespan. Obviously a very difficult problem. And so you may look at these features, these 8 features, and say, well, actually, maybe lifespan is not a good idea if you have their age. Maybe years remaining. Years remaining. Okay. Or I'm not. That's too morbid. Lifespan. And take this out. Let's just pretend age is not here, because that would not be. That would not. Actually, that's not true. Age would be, because what's interesting, and this is an aside, but if there's this curve. This is not machine learning, but it's biomedical, so I'm going to throw it in here. This is birth year. And, oh, God, you're stupid. And this is lifespan. And so, first of all, what do you think this curve should look like? Any ideas? If you're feeling, if you got a case on the Mondays, you can put your answers in the chat. What do you think of the curve of birth year versus lifespan looks like?
Should be basically increasing.
Yeah, it should be baseline. I mean, that's definitely, yeah. So right, that's a very, very sensible guess, right? So maybe it's flat, right? Because it doesn't matter, whether you're born this year, next year, it doesn't really matter. However, over time, there is actually a linear relationship. So if you think about this from, on a very long time scale, right? People are living longer now than they were in the whatever medieval times and 2000 years ago. So there is actually there's a predicted linear model. Let me see if I can undo this. It's actually a very interesting thing to think about. This is like an epidemiology thing. There is some predicted model. I don't know what the slope of that curve is, but basically for every year that goes by, the average human lives, some amount longer on average. But what's really interesting is that actually, what they're finding now is that the model needs to be refined, because there is a systematic kind of shift for the data to be above this curve. And so and this is pre-COVID, by the way. So I don't know. I know that COVID actually reduced lifespan worldwide, but there's if there's more data points that are above this line than there are data points below this line. And so something is happening where people are living longer on average, then their birth year would predict, with the linear model that the statisticians have in place, right? So, your kids.
Wouldn't that just mean that it's not a linear relationship?
Yeah.
Like that's the wrong model.
Yeah, I mean, it could be that it's not linear. It could just be that this. Yeah. Actually, that's actually a really good insight. That's definitely one possible interpretation. That the model just isn't. It's just not a linear relationship. Yeah. I've heard a statement of this phenomenon very recently, but I haven't actually heard. When I was listening to this, I didn't actually hear what their takeaway was, or what they think this means, or what variable it is that's causing that. I mean, there's obviously modern medicine. There's there's a myriad of things that could be contributing to this, and definitely it's possible that there's a nonlinearity in this relationship. The longevity buffs will probably have you believe that undo that. So David Sinclair, who I am a fanboy of, will have you believe that there are people on the planet today that will live to 150. And so, yeah, and the longevity folks will have you believe that this curve would, is set to blow up, any year. And so let's hope they're right, but jury's still out. But yeah, I didn't want to erase all that. Anyhow, I'm gonna draw, because I think this is actually a good example. So actually, age could be a predictor of longevity. I was wrong to think that. It doesn't make sense. It actually does make sense. HRV, caloric, I had exercise frequency, and I had daily caloric. As a public service, I'll just let you guys know that caloric restriction, and if I've said this, I apologize. Caloric restriction is probably not the only, but it's the intervention that for sure increases longevity in basically every species that has been tried in. Caloric intake leads to a 20% longer life. And so that would probably be a good predictor here. And so what I'm getting at here is with kernels is that, yeah, okay, I may want to weight each of these 8 predictors to predict lifespan, but I also may want to do things like this. I may think that it's not your exercise frequency or caloric intake. Maybe it's the square of frequency or the cube, or maybe it's the product of exercise frequency and daily caloric intake, right? So that would be called an interaction. So maybe you think that there are interactions between these variables. And so how do you capture that in this framework? Well, the way that you capture it is with this mapping phi. So phi is not the kernel, but it's very related to the kernel. Kernel is a very satisfying word to say. I don't know why, but that's neither here nor there. So phi is a mapping from your feature space, from your, to a nonlinear space. And there's a problem with terminology here, because sometimes the word feature now is just used to denote the data that you collect to make predictions with. But like 20 years ago, feature phi was called the feature, actually, which is kind of confusing. But essentially, what phi is doing is it's mapping these variables into a new set of variables something like you'll have height times weight or something, or age times BMI, or age to the power of 4. I don't know, something crazy like that. It could be anything. And then you do your, so first you transform your X into this 5-vector, and then you do your inner product, and then you do your similarity mapping. So you don't just look at when a new data point comes in, you do not measure similarity in the specific form the data comes in. First, you transform it into this new feature space, and then you compute what's called the kernel. And the kernel is just what we saw before. It's just that before it was just X transpose Z, and now it's phi X transpose times phi Z. So what phi is doing here is it's taking your original features and it's kind of expanding them. And it's always going to be, so the dimensionality of phi is always going to be larger than the dimensionality of X. So you're going to have more features in this new space, not less. The idea is that you want to capture more information. All right, so let me give you a kind of a concrete example of this, what one of these phi could be. So one of these kernels could be. So the simplest possible kernel is this. Instead of just taking the inner product, you take the square of the inner product. And it seems really, it seems kind of silly. Like, why are you doing this? Why would you want to do, like if you're taking the inner product and you're using that as a similarity, what difference is it if you square it? Well, actually there is a difference mathematically. And the difference is that now you are, and when you work this out, so if you, the inner product is just, you know, xi times zi summed across all features, and now you're going to square it. So when you expand this out, what you see is that you've transformed, the squaring operation has transformed your inner product into another inner product that is now taking all pairwise combinations of features. And so, for example, this will be age times height or something. This would be age times BMIs, or like if here you have only 3 features. So if you have like, let's say you have weight, age, and caloric intake. So this would be all 9 combinations of those 3 variables that are now getting assembled into a new feature vector phi. And so what this kernel has done is it's allowed you to compute a similarity measure between feature vectors that consider interaction terms, right? So you're not looking at when you're making predictions on someone, you're not making that prediction based on how much they weigh or how much they eat or what year they were born in per se. You're making predictions on the combinations of those variables. So you're looking at interactions, only interactions. And so the kernel here so if you have 2 data, you have two features. Again, the feature word is problematic here. If you have 2 examples, X and Z, instead of when you want to compare how similar they are, first you take the regular inner product and then you square it. And that becomes your similarity measure. And so a very related kernel is called, well, it's just, this is a quadratic kernel, but now with an intercept term, with an offset. And the reason that this offset is helpful is that, and again, I'll leave it to you guys to verify that the math is correct. I assure you it is, in the sense that now what you have is you have the same thing as before, but you also have these linear terms. And so when you use this kernel, the corresponding phi representation is what we saw before, which is all 9 combinations of your 3 features, plus, and this is a typo, let's just say x1, x2, and x3. I apologize for that. Plus your original features, essentially. And the C, don't worry about the C here. All it's doing is just scaling your data, but that does not affect behavior of any learning algorithm. And so the reason that this is nice is because now your features are looking at both interaction terms and regular terms and an intercept. And so this is like these 3 elements here, which should say x1, x2, and x3. This is your standard SVM. And then these 9 up above, those are your interaction terms. So with this kernel here, your classifier is looking at both just the regular old data and also interactions between all your features. And so it's now you have a richer set of features. And the kernel trick is that you never end up computing phi. And this is the thing that is confusing to people. Phi is implicitly computed when you measure the kernel. So the kernel, all it is a function, input-output function that takes in two data examples and outputs a real number and outputs a single number. And that single number, first of all, is always positive or 0. It can never be negative. That's really important because it has to measure similarity. And it wouldn't make sense to measure similarity if you could have negative values. Give me just a second. Okay. So the kernel is what you actually compute. The phi is what's implicitly being used in the computation of the kernel to represent your data examples X and Z. And so, for example, this phi X, which is 13-dimensional, you don't actually have to compute it. You don't actually have to transform X into phi of X, then transform Z into phi of Z, and then do this, and then do the inner product. You don't actually have to do that. That's automatically done when you do this. When you just take your inner product, add a positive number to it, and C could be anything you want, and then square it. And it's called a trick, and you'll see why, is because for certain kernels, this phi actually has an infinite number of elements. And that's why it's called the trick. So you essentially, you can take your data and warp it to an infinite dimensional space, measure similarity in that infinite dimensional space, which you could never actually do explicitly, because obviously you cannot represent your data in an infinite dimensional space on your computer. And so the kernel trick is that the computation of the kernel doesn't actually require you to evaluate phi. Phi is invisible to you. And so phi, you can basically come up, you can come up with any kernel you want as long as it has certain properties, which we'll cover in just a second. And every kernel basically corresponds to some mapping phi of your data. And I think the thing that's confusing, one of the areas where people can get lost here is that phi is operating on a single example. So if you have an X, if you have a brain scan, and vector X is a collection of all the intensities of every voxel in the brain scan, what the phi function is doing is it's basically making a new set of voxel intensities that has some like interaction terms and maybe other kind of combinations. And so, but it's not actually being computed. All that you're computing is the similarity between data examples with this new kernel. And this kernel allows you to capture higher order moments of your data. So it's allowing, like as we saw previously with the polynomial, with the quadratic kernel, we saw that the quadratic kernel was capturing quadratic terms, and you can also capture cubic and quartic, et cetera, et cetera. Computationally, this is nice because this notation means order of. Order of just means which multiple of 10 are you closest to. So this means that if you have 100 examples, you would have to do this. If you had to compute this explicitly, you would have to perform in the order of 100,000 operations. But by using this kernel measure, you're reducing that down into just a number of computations is in the order of your data set, which is very nice. I mean, your data set could still be large, which is all the more reason why you don't want to have to compute 100 million squared computations when you implement support vector machines. Okay, and this is the most popular kernel. This was like I would argue the kind of the state of the art really before. I mean, some people will say that before deep learning, something called random forests were the state of the art. Random forest, it's a kind of a silly name. There's something called decision trees, which I hate. But decision trees are they're an architecture in machine learning. And I'll tell you a little bit about decision trees quickly here. Basically, you look at each feature, and if the feature is bigger than this, you say cancer. If you say malignant. If the feature is smaller than this, you say benign. And then you keep repeating that, and that forms this tree-like structure. And it's like your classification problem has been converted into kind of like a flow chart. It's very heuristic, but it works well in some problems. And so the reason I bring this up is because either that kind of decision tree methodology or this equation here, this version of the support vector machine, was kind of what everyone did before deep learning came around. And so what is this Gaussian kernel? It is also called the radial basis function, or RBF. So you'll come across this a lot in the literature, radial basis function. So what is it? It's essentially a similarity measure that between two data points, X and Z. And what it does is it looks at every dimension, right? So if you think about, let's see, how do I wish I had a board for this. Let me see if I can. So if you think about what this is doing, oops. What this really is you have x1 minus z1 squared plus x2 minus z2 squared plus dot 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 xd minus zd squared. Okay, so this is it's a sum of squares, and you don't have to square root it because it's already, this is called L2. There's the L2 norm, basically Euclidean distance between x and z squared. So geometrically, what this kernel is doing is that if you have two data points, two data points, and you want to measure the similarity between them, you just use your standard Euclidean distance between them squared. So your similarity measure is basically, actually, let me ask you that. Let me see if I can get some of you involved here. So how do I ask this question without giving it away, without making it too hard? Okay. The problem, the kind of the way the cartoon that I've always been showing you to this point is something like this. You have, and I mean, not just, this is any machine learning. This is kind of what, this is the picture that everyone shows. You have two classes, right? And you want to separate them. You have something like this. Here, so this is like the standard kind of methodology. You draw a hyperplane that separates two clouds. So this picture here on the right is very different. Sorry. It's quite different. And so what's the, I guess I'll ask it the way I was going to ask it. So what is the big difference between this methodology, like the logistic regression, the linear supported vector machine, and this methodology where you're basically, so in the methodology on the right, you're just looking at, distance between every pair of points. So I guess when how would you decide on a given problem whether I should do this, separate two clouds with a line of the hyperplane, or whether I should do this, where I basically look at how close I am to the training examples? What's the big difference between these two pictures? Any ideas? So notice that, oops, I won't do that. So the one thing, I'll get rid of this. The one thing that is really, the distinction is that in the picture on the left, the direction of your feature vectors, so their orientation, really matters, right? So essentially what you're saying is that the difference between a benign brain scan and a malignant brain scan is that if you plot them in, in high dimensional space, they occupy, they have different orientations geometrically. So they're, how do I say this? So let's think about two voxels, so two intensities. So the malignant brain scans, and let's say that voxel 1 will be the horizontal axis and voxel 2 would be the vertical axis. The methodology here is that a malignant scan is one where voxel 1 is very bright. So maybe it's a part of the tumor that, I don't know, is in the glia or something. So there's, GBM, glioblastoma is the most common type of brain tumor. And so maybe voxel 1 is covering the glial tissue. And so if you see a very large, intensity in the glial tissue, then that may indicate that you have, this is a malignant brain scan. This is a brain scan of a malignant tumor. And then the other thing here is that somewhat voxel 2, which is the vertical axis, generally, if voxel 2 has a high intensity, then you're more likely to be malignant, right? So it's kind of a combination of that. You look at how bright voxel 1 is and how dark voxel 2 is. So a brain scan that has a bright voxel 1 and a dark voxel 2 is more likely to be malignant. Now, the picture on the right is kind of saying something different. You're saying there isn't necessarily that kind of a relationship between the malignant tumors and the benign tumors. Rather, you just kind of have these clusters in space. So, if you may have, some cluster of, you have maybe a cluster of malignant tumors out here, and then you have another cluster of, sorry, benign, it was the blue, and you have another cluster of malignant tumors out here. So directionally, there are malignant tumors that have the same direction as the benign tumors. What differentiates two classes here is not the direction, but it's the overall magnitude, it's the radius. That's why this is often called a radial basis function. So what you're doing here is you are literally comparing how close you are to the training set. So that's one thing. The second thing is that it's not just, you're also applying this Gaussian transformation to it. So what is the Gaussian doing, right? So if you have the Gaussian curve, if I have it's a one-dimensional curve here. So my Gaussian, is gonna look, maybe try to draw it, something like that. So, and this would be 0. This would be the mean. And so when you're very close, when you're very close, when X and Z are very close, then this mapping, this exponential mapping, will give that kernel a large weight. But if you're very far away, if X minus Z if the distance from X and Z is very far away, then the kernel's gonna assign it a very low magnitude out here. And so what it's doing is it's really putting a premium on the data points that are close to you. In that, and it's all, you have control over that also with the sigma parameter. So you choose sigma, by the way. Sigma is a property of your kernel that you get to tune, and generally you will tune it to kind of get the best performance on your test set with cross validation. And so what this Gaussian kernel or radial basis function is doing is it's really placing more importance on the examples in the training set that you're close to. Okay. And on the next slide, I think you'll see that there is, okay. If you use a Taylor series expansion for the exponential function, you see that the corresponding phi function here for this kernel is actually an infinite dimensional vector. So computing this Gaussian transform distance between two vectors X and Z is equivalent to doing an inner product in infinite dimensional space. And so I think this is one of the cool, appealing things about this kernel is that now you're taking your data and you're warping it to infinite dimensional space. And one advantage of taking your data in this infinite dimensional space is now all of a sudden your data is always separable. So in 2 dimensions, you know, basically, I'll try to I'll try to draw something with 2 dimensions and 3 dimensions, and I'll try to convince you of this. So if you have 2 classes in 2D, you know, it's rare that you'll be able to always, you know, like for example, this we're going to talk about this. This is called the XOR problem. These are not separable with a linear classifier in 2 dimensions. But now if you go to 3 dimensions, you know, it's you're more likely, and again, the mathematicians will cringe at this, what I'm saying is that in 3 dimensions, you're more likely to be able to separate this kind of configuration. As long as there's some separation in the Z plane, well, already you're starting to see that you're more likely to be able to draw a plane that separates the 2 classes. And if you keep going to 4, 5, and infinite number of dimensions, what you see is that your data set ends up being more and more separable, which is very nice because the entire support vector machine math that we saw last week is rooted in this assumption that your data is separable. Okay, so the important thing here is that the Gaussian kernel is effectively warping your data. It's creating a new vector of features that has an infinite number of elements in it. And then once you're in that infinite dimensional space, then you do your inner product. But you don't actually have to do that because of this kernel trick, because this exponential function automatically does that for you. Okay. So one question then is, and I mentioned that, you know, you can come up with your own kernel. So if you think that there's a similarity measure that would work well in your data, there's the support vector machine machinery supports that. So you can do this, you can use any kernel you want basically. And if you choose your kernel sensibly, there is some measure phi that corresponds to that kernel, right? So you choose K and phi comes out of it. And so there's only 2 things basically that you have to guarantee. One is that the similarity between X and Z has to equal to the similarity between Z and X. Otherwise, you're not measuring similarity, right? Obviously, if there's an order dependence, then it's not really similarity. It wouldn't make sense. The second thing is that it has to be non-negative, right? And that's, again, just kind of, you know, intuitively, it doesn't make sense to have negative similarity. You can have no similarity, or you can have some similarity level. And so as long as you satisfy these 2 things, you can use that kernel. And so in practice, what you end up doing is you end up forming the kernel matrix. And so the kernel matrix is between points in your training set, not features. Okay, so essentially, if you have a training set that has 3 elements in it, then you have a 3x3 kernel matrix. And this has to be a symmetric matrix. So this element has to be the same as this element has to be the same as this element, etc. And the other thing is that if you view this as a matrix, then if you treat this as like the coefficient of a quadratic, that quadratic always has to evaluate to a number bigger than 0. It cannot evaluate to be negative. So this is called Mercer's theorem. I don't really teach it formally here because I don't think it's I don't think it's that important for you guys, but there's a theorem that says that as long as you satisfy this property, then your kernel K is a valid kernel, and you can use it in a support vector machine, and you can make your predictions with it. Okay, so I don't want to go on in the slides. What I want to do now is, the last thing I'll say, I'll go back actually and just remind you that essentially what kernels do is, so this this inner product here is essentially replaced with a kernel operation. And so you don't have to do your regular inner product. You can be more fancy and go with a kernel. And there are many problems where, for example, using a Gaussian kernel will get you better performance. And so what I want to do now is just use the remaining time here to kind of show you how to implement this in MATLAB. So both demo kernel SVM and demo kernel SVM2 are on Blackboard. We only have 11 minutes. So the goal of this is just to show you the API for this. So fit CSVM is a MATLAB, it's kind of a flexible MATLAB function for performing classification with support vector machines. So by the way, you can also do regression with support vector machines. So if the thing that you're predicting, for example, in the lifespan example, that's really a regression problem because lifespan is, it's a continuous number. And so there's a version of this function that applies for regression. But fit RSVM is the regression, but fit CSVM is for classification. And so what do you pass to fit CSVM other than your data? And so what you pass, as you probably, let me see if I can scroll down to where you choose your kernels. Right, so let's keep going. I'll show you the different kernels that it gives you. Right, here we go. So there's an option here called kernel function, and that kernel function, there are some plug and play options. So you can do a Gaussian or RBF kernel. You can do a linear kernel, which is that's your, like, if you want to separate your data with a linear hyperplane, or you can use a polynomial kernel, which is what we saw with the quadratic case, or you can actually make your own. You can pass MATLAB basically a function that evaluates your kernel for MATLAB for this function. And so what I'm going to show you in this example is basically the result of classifying a data set with all three possible options of these. So what's different about these three is just the way that you're measuring similarity. So this is, you're just looking to see how close you are to the example, Euclidean distance. This one looks at, what direction your data point has. And this one is, the polynomial is the one that's kind of, in a sense, is the most powerful. It overfits very quickly because polynomials, I think I've shown you some cartoons of fitting a polynomial to a curve, and you can see how if your polynomial has too high of a degree, it's very easy to overfit. And so polynomial kernels are probably the choice that requires the most data. You really need to have a lot of data to use a polynomial kernel. But what I'm going to do here is I'm going to take my arrhythmia data set. The first thing I'm going to do is just load it in. And I see that I have a 452 example data set where each example has 279 dimensions. And out of the box, this comes out as this, there's 16 different classes. We've seen this before. And so what I've been doing to convert this to a binary problem is just saying that after throwing out all the inconclusives, I said, if you have an arrhythmia, you belong to class 0. And if you don't have an arrhythmia, if your ECG is normal, you're class 0. And if you do have an arrhythmia, no matter what kind it is, you're class 1. And then that becomes Y2. And now if you look at unique Y2, we'll just have zeros and ones. You see that we have 430 examples left. And out of those 430 examples, 43% of them correspond to arrhythmias. So now we're going to move on to our cross-validation loop. So in this cross-validation loop, what I'm doing is I'm extracting the training data for each fold. And then I'm passing that training data to 4 different training routines. So it's the same call, except with a different option for the kernel. So this is your standard maximum margin hyperplane. This is your Gaussian radial basis function. That's the infinite dimensional phi. And then I'm going to train 2 different polynomials. I'm going to train a polynomial of order 2 and a polynomial of order 3. And so I'm going to run this to here. So I'm going to step through. I've trained my linear SVM. I've trained my polynomial SVM. And now I've trained my Gaussian SVM. So let's look at, these outputs of these training calls are now, these are objects. And so an object has different fields that you can access. And what I want to show you is, so first of all, notice that our training set has 344 examples, and our test set, oops, there's no test set yet. Well, the test set will be whatever is left over between 430 and 344. And so, let's see. So one of the things that, hold on. So one of the fields that I want to kind of draw your attention to is this is support vector. Right, so this is the is support vector field is a binary it's a binary variable that indicates whether or not that data point was one of those close to the boundary examples that is really important in the prediction. And I'm trying to understand. I don't understand why why it only returned 55 and not 344. And I will see if I can. Kind of weird that it's almost as if it truncated our data set somehow without us. Let me try again, make sure. I have no idea why 54. It must be, let's see. Pro- See if I can get. See, now we can get. Huh. It's done something. It's pre-processed our data for some reason to so let me I have a feeling that see if I do this. We haven't gotten to what the box constraint is, but no. The only thing I can maybe there are nans in the data. I don't know. Oh, that's probably what it is. Okay. Okay. Let's see. My guess is that they're oops. Let's see. Okay, hold on. My guess is that there's 54 examples that don't have a nan in it. Hold on. Is nan extreme? Oh, that's fine. Why am I blanking out on this? Hold on. What I want to do is count the number of maybe image scale list. So these here are examples and these are the features. And I'm trying to see. Yeah, so there is one feature here that is causing this problem. There's this data set has not a number means missing data. And there's a hack to this, which I'd never recommend you do. But I'm going to do it here. I'm just going to set it to 0. And I'm going to see if this solves. Actually, you know what? Let me do it initially to the X. So what I'm doing in this line of code is everywhere where my data is missing, I'm just going to set it to 0. And I'm going to see if this solves the problem. It's taking longer too. Right. Okay, so now it did in fact solve the problem. So now my is support vector has, so I can see that. So there, I have 133 support vectors in this data set out of 344. Those are the 133 that are really important. I realize at a time, so all I want to do is just run this through now, and I'll show you which of these 4 methods work the best. Hopefully we have time. So linear worked best on the first fold. Also for the second fold. Keep in mind that now we're basically falsifying that one dimension, which is a problem. Replacing not a number with 0 is bad because 0 means something. Zero means, you know, it's the actual data was not 0, it was some number that is not available to us. But as is usually the case in biomedical data sets, the linear classifier here works the best. And so if I do my So 67% accuracy for the regular SVM, 57% for the Gaussian kernel, and I think even worse performance for the poly. 40% for degree 2 polynomial and 57% for degree 3 polynomial. So I'm gone over. Thank you for letting me go over. I will see you guys Wednesday, where I will continue trying to teach you guys about kernels with some more examples. Bye-bye.